So this is the input and this is my objective, the output. Okay, so I will start from the PowerPoint presentation. So I will have, this is the okay, so this is the model. This is the model of the Doubly-Fed induction generator. What is the difference with the induction motor? I will have a second voltage source. Okay, the only difference between the induction motor and the Doubly-Fed induction generator is I have this voltage source, because in the rotor I will have the converters, right? And this is the stator voltage. This is the only difference. Okay, so I will apply Kirchhoff voltage law in this loop. I will apply Kirchhoff voltage law in this loop. Therefore, I will get my first and my second equation. Okay. Later on, I will have the real part and the imaginary part. So separating the real and the imaginary part, I will get these four equations. Equation number 1, equation number 2, 3, and finally equation number 4. Okay, so I will have these four equations. Okay, so let's start the initialization. Okay, so I will have, this is the equation number 1. Okay, this is the equation number 1. This is equation number 2. I will have here the equation number 3. And this is the equation number 4. Okay, so let's start with the first part of the initialization. Okay, what is known and what is unknown? What is data? Okay, what is data? So I will have the data is the stator voltage. Okay, I will have the angle. This data come from the initialization of the power grid. Okay, so this is the reference set points. This is data. Okay, so pay attention to this part. Let's make a look. Let's make a look for the initialization of the power grid. Okay, so pay attention to this part. This is the active power grid and this is the reactive power grid. This is my objective. Okay, this is my objective. Okay, so what else? I will have the stator reactance. This is data from the manufacturer. The stator resistance. Okay, the magnetizing inductance. I will have the rotor reactance referred to the stator side. I will have the rotor resistance. I will have the design, the constant. This is a constant of the machine. This data come from the design of the machine. This is a data too. Okay, so what is known and what is unknown? So I will have the rotor. The rotor voltage is unknown. So I will use data from the voltage angle. I will use phi from the current angle. Okay. So this is the voltage. I will have, this is unknown. I will use phi. Okay, this is referred to the stator side. What else? I will have the stator current and the angle. Okay, this is unknown. And finally the slip. So I will have 2, 4, 5, 6 unknown. Okay, and this is data. Okay, so from the previous initialization, we know the stator voltage. Okay, so I will copy here. I will copy here the stator voltage is equal to 1.037 499, and the angle from the initialization is equal to 23.111 39 degrees. So this is data 2. Okay, so substituting the values. Okay, so substituting the values. In my first equation, I will have the stator voltage is equal to 1 point. I will have 37 499 cosine of theta. In this case, the angle is 23.111 39 degrees. Okay. Yeah. Okay. The stator resistance is data. Okay. The stator resistance is data. So plus I will have 0.00779. The current is unknown. Okay, I will have the current sign. Yeah, I will have this is unknown too. Okay. Okay, so I will have here the stator reactance plus the magnetizing reactance. Okay, so I will have plus. So I will have 0.0. I will have 79. 37 plus the magnetizing inductance. According to the manufacturer, this value is 4.1039. Okay, times the stator current sine of the angle. Okay, sine of the angle. Okay. And the last term is the magnetizing inductance. The magnetizing inductance is 4.1039. Okay, I will have the rotor current. This is unknown. And the angle. I will have sine. Yeah, this is my first equation. Okay, what about the second equation? Once again, substituting the values, I will have the stator voltage. We have already computed in the initialization of the power grid is equal to 1037,499. Okay, I will have here sine, the angle is 23.111, 39 degrees, plus this term, I will have the stator resistance plus 0.00779. I will have the stator current, this is unknown, and the sine of the angle is unknown too. Okay. Later on, I will take the stator reactance. The stator reactance in this case is 0. From the manufacturer 0.0. Okay, I will have 0.07937 plus. Okay, I will have the magnetizing inductance 4.1039 times the stator current sines the angle, sines of the angle. Okay. So I will have cosine. Sorry, this is cosine. Okay, so I will have here the cosine. So is cosine minus. I will have the magnetizing reactance is 4.10. I will have 39. This is the rotor current. Cosine, I will have the angle. Okay, this is equation number 2. Okay, let's continue with the next equation. I will have equation 3. So I will have the voltage. This is the rotor voltage cosine theta. Okay, I will have minus. This is the slip. Okay, so I will have the slip times the magnetizing inductance 4 times 1039. The stator current sine, I will have phi. This is the angle. Okay. Later on, the next term is the rotor resistance. I will have 0.0082. I will have times the rotor current. Okay, I will have times the rotor current cosine. I will have the angle. Okay, I will have the angle. Okay, plus I will have the slip times the rotor the rotor reactance. Okay, the rotor reactance according to the manufacturer is 0.4. Okay, plus the magnetizing inductance 4.1039. Okay, times the rotor current cosine, and this is equal to 0. Okay. The next equation. So once again, I will have here the rotor voltage times sine of the angle plus this is the slip. Okay, the magnetizing inductance is 4 times 1039 times the stator current. I will have here cosine. Okay, minus I will have the rotor resistance times the rotor resistance. We know this value. Okay, so the rotor resistance is 0.00 82 times I will have the rotor current sine. I will have here sine of the angle. Okay, and the last term is minus. I will have here the slip. I will have the rotor reactance 0.4 plus the magnetizing inductance 4.1039 times I will have the rotor current referred to the stator cosine, and this is equal to 0. So far I have 4 equations and 7 unknowns. Okay, so far I have 4 equations and 7 unknowns. Okay, so therefore I need more equations. Okay, so the next equation comes from the power balance. Okay, the next equation comes from the power balance. Okay, so I will have, for instance, what is the power balance here? So I will have, this is the power grid. Okay, so the next equations come from the power balance. Okay, so for instance, I will have here the power grid, the active power grid, and the reactive power grid. Okay, so I will have here the stator active power and the stator reactive power. And finally, I will have here the rotor active power and the rotor reactive power. So the power grid is equal to the stator active power plus the rotor active power. The reactive power grid is equal to the stator reactive power and the rotor reactive power. Okay, so for the control viewpoint, this is a control strategy. I will assume the rotor reactive power is equal to 0. In order to carry out the control. This is a control strategy, but it's possible to assume a different value. Okay, for this case, I will assume the rotor reactive power is equal to 0. Once again, this is a control strategy. Okay, this is a control strategy. So let's continue. So applying the power balance, so I will have, this is the power grid, the active power grid. This is the reactive power grid. So once again, the active power grid, okay, is equal to the stator active power plus the rotor active power. And the reactive power grid is equal to the stator reactive power plus the rotor reactive power, assuming this value is equal to 0. Okay, so therefore I will have the stator power is this term, and the rotor active power is this term. So this is equal to 0. What about the the reactive power grid. If this is 0, okay, so I will have the grid active power is equal to the stator active power, okay, and the rotor reactive power is equal to 0. So this is the stator active power, this is the rotor, okay, this is the stator, and the rotor is equal to 0. Okay, so this is the power balance equation. Okay, so the expression from the active and reactive power injected into the power grid are this active power and this reactive power. Do you remember this is data, right? This is data. Okay, so let's start with this equation. Let's call this equation number 5. So let's work a little bit on equation number 5. So the active power grid, this is the reference set point, okay, is equal to 0. I will have 900 for 977. This is the reference set point, okay, minus I will have the stator voltage, this is data, 1.0, okay, 37, 499, okay, times the stator current. I will have here cosine of theta. This is the angle for the voltage, okay, but I have power, okay, so I need to include the angle of the current too, okay, so I will have here, this is 23.11139. So this is power, yeah, and this is only the angle for the voltage, okay, so I need to include the angle of the current because it's power, okay, because it's power. Okay, so plus I will have this voltage. This voltage is unknown, okay, times the rotor current. I will have here cosine, this is theta. This is unknown, okay, but I need to include the angle of the current because once again I have power, okay, and this is equal to 0. This is equation number 5. This is equation number 5. Okay, so let's call this equation number 6. Yeah, for equation number 6, I will have, this is the reference set point, okay? So I will have equation number 6 is equal to, okay, so equation number 6. This is the equation number 6. So I will have the reactive power reference set point is 0.271, okay, 493 minus, this is the reference set point, okay, minus the stator voltage is 1.0. I will have 39,499 times the stator current sine, okay. I will have here the sine of theta s, okay, so I will have theta s is equal to 23, okay, so I will have 23.11, 111, 39. So once again, I need to include the current angle, okay? So I will say minus, and I will have, because it's a power, okay? Because it's a power. So I have 6 equations and 7 unknown. So it means one equation is missing, okay? One equation is missing. Okay, so the last equation, we need to remember the mechanical power is the sum of the stator and rotor powers injected into the power grid, including active power losses in the windings, okay? So the last equation comes from the mechanical power, okay? So the mechanical power is here, okay? Is the sum of the stator and rotor power. This is the stator power. This is the rotor power, okay? Injected into the power grid, but I need to include the active power losses in the winding. So this is the active power losses in the winding. Okay, this is the active power losses in the winding. So with this, I will have 7 equations, but let's make a loop in this equation. Let's make a loop. I will have one unknown. This is 8 unknowns. Okay, I have only 7 equations. Therefore, I will use this approximation. This is this function. Okay, the mechanical power is equal to this constant. This is data. This data comes from the manufacturer. This is a design constant of the machine. 1 minus the sleep to the power of 7. Okay, so I will substitute. Substituting in this equation the mechanical power. Okay, so I will have, substituting this term, I will have the constant time 1 minus the sleep to the power of 7. So now I will have 7 equations and 7 unknowns. Okay, so this is data. I will have 0. I will have 47, 15. I will have 85 times 1 minus the sleep to the power of 7. Okay, minus the stator voltage is 1.0. I will have 37,499. Okay, times the stator current. Okay, so I will have a cosine of 0, and this is the angle is 23.111. 39, I need to include, because it's power, I need to include the angle of the current. Okay, I need to include the angle of the current. Okay, so I will have minus, I will have the rotor, voltage, the rotor current. I will have here cosine. This is theta. So once again, I need to include the angle of the current because I have power, okay? So including this angle, minus, I will have the stator resistance. The stator resistance is 0.00779 times the stator current. This is the active power losses, okay? Plus the rotor. Okay, the rotor resistance is 0.0082. I will have the rotor current prime square because it's the rotor active power losses, and this is equal to 0. Okay, so I have 7 unknowns. I have 7 equations. 7 by 7 equations. Okay, but this is, I need to solve the nonlinear equations. Okay, I need to solve the nonlinear equation. Okay, so for that, I need initial conditions. Okay, I need initial conditions. Okay, I will copy this equation, for instance, in MATLAB. I will use the solver of MATLAB. Okay, I will use the solver. I will compute the 7 unknowns. Okay, so what are the initial conditions? I will assume. Okay, I will assume for the rotor voltage 0.1, for theta 0.1, for the current 1, for phi 0.1. Okay, the stator current 0.1, the angle 1, and for the sleep 0. You can assume any value. Okay, you can assume any value. I will assume this value. I will use the solver of MATLAB because I need to solve nonlinear equations. Okay, so solving these 7 by 7 equations, okay, I will get the following result. Okay, so I will have the rotor voltage. Let's copy here. Yeah, the rotor voltage is equal to 0 in per unit values, okay? 0.127, 856 per unit. Okay, what is the angle? The angle is theta for the voltage, okay? In this case, the angle is in radians, so I will have negative 2.395, 13, and this is radians. Okay, this is for the voltage. What about the current? So I will have the current in per unit values 2. I will have 0.966, 718 per unit. Okay, I will have here the angle phi. And this angle is in radians, so I will have negative 0.165, 886 radians. Okay, so I have 4 unknowns. Okay, later on I will have the stator current. The stator current in per unit value is 0. I will have 841, 0.52 per unit. What about the angle? The angle for the current is phi. Okay, so I will have 0.086, 984, and I will have radians. And the last variable is the slip. And for the slip, solving the 7 by 7 equation, I will have this is equal to 0.099, 857 per unit. Okay, this is the solution. This is the solution of the single-phase equivalent circuit model of the Doubly-Fed induction generator. Okay, this is my first step. So I need to work in the stator side. Okay, I need to work in the stator side. Okay, so let's work on the stator side. Okay, so I will say electrical quantities first of all. So I will have the electrical speed. So pay attention, I have the voltage. In the initialization of the power grid, I compute the stator voltage and the angle, right? So what I know is the voltage on the stator, the voltage on the rotor side, the current, and the angles. And besides, I know the slip, okay? In order to complete my first step, do you remember my first step? Yeah, my first step is from the natural reference frame, I need to convert to the part transform. I will use the part transformation in order to have the QD0 reference frame. Okay, so far I have only the natural reference frame. I need to convert to the part reference frame. Okay, so let's work in this part. Okay, so the stator, this is the electrical speed. Okay, the electrical speed is equal to 2 times pi times the frequency. Okay, so for this case, the frequency is 60 Hertz. Okay, so therefore I will have the electrical speed is 376.991 electrical radians per second. Okay. Okay, so because I have per unit values, what I need is actual values. Okay, so by definition, the per unit value is equal to the actual value over the base. Okay, I need the actual value, so solving for this voltage, isolating, I will have the per unit value times the base in order to have the actual value. Okay, so therefore I need to select a base. Okay, so I will have the base voltage. This is the subscript S due to the stator. Okay, is equal to, I have the line-to-line voltage. What I need is the line to neutral voltage. That is the reason, divided over the square root of 3. Okay, so the output voltage of the generator is 690 volts over the square root of 3, and this is equal to 398, okay, 0.372 volts. Okay, therefore the line to neutral voltage, I will convert to actual values. Okay, so the stator line to neutral voltage is equal to, this is the actual value. Okay, this is the actual value. So I will compute the per unit value 1.037 499 times the base, and the base is 398.372 volts. This is the base, right? And this is the per unit value. Therefore, I will compute the actual value. But this is the line to neutral voltage, okay? So I will get 413.311 volts. Okay, 311 volts. What is my objective? My objective is to compute to convert from the natural reference frame to the part reference frame. Okay, so therefore, using the part transformation, this is for the stator side. Okay, this is the part reference frame is equal to the transformation matrix times the natural voltage reference frame. Okay, so that is the way in order to convert to QD0 reference frame. Okay, so therefore I have only the magnitude, right? I will have in actual values because I have a three-phase system. Okay, so let's back to the three-phase system. For the stator and from the rotor, I will use the same. Okay, so this is from the stator. This is the formula, right? So I will have 100. If this is the reference, I need to have a 120 degrees of phase displacement for the other phase, all right? So this is for the stator. This is for the stator. Later on, I will work in the rotor. In a similar way, if this is the reference, because I have a three-phase system, I need a phase displacement of 120 degrees. Okay, this is for phasor B, and this is for phasor C. So let's start with the stator. Later on, we continue with the rotor. Okay. So we have the magnitude, and this is the magnitude. Okay, using these formulas, I will have the stator. This is phase A. Okay, is equal to the square root. I will have the stator. This is the line to neutral voltage. Okay, cosine. I will have omega t plus theta. Okay, plus 0, because it's the reference. Okay, this is the reference. Okay, this is the stator voltage, and because I am working at steady state conditions, this time is 0, because I am working on steady state conditions. So far, any question? Mrs. Sola, do you have any question? Did you get it?
It's clear, doctor. Thank you.
Okay, so let's continue. We know now what is my objective. Okay, this is phasor A. Because I have a three-phase system, I need a phase displacement of 120 degrees. So I will have the square root of 2. This is the line to neutral voltage. Okay, I will have here cosine omega t. Okay, plus and now I will have the 120 degrees phase displacement. This is for phasor B. And finally, for phasor C, okay, I will have the square root of 2. This is the line to neutral voltage cosine. Okay, I will have omega t, okay, plus theta s plus 2 times pi times 2 times pi over 3. Okay. So substituting the values, this value is 413.311. Okay, so I will substitute 413.311. This is 0 because I am analyzing the steady state condition. This data is in radians, and this value is 0.40337. Okay, so I will have this is 0. I will have 413.311. Okay, this is in radians, so I will have 0.40337. Okay, the same here. This is 0. This is 413.311. This angle comes from radians. This angle is in radians, so we will have 337. Okay, so let's compute for the three-phase system what are these values. Okay, so for phasor A, I will have here, this is 537 point. I will have 598, 345 volts. Okay. Yeah, for phase B, I will have negative. This is 70.150, 367 volts. And finally, for phasor C, I will have negative 467.492, 978 volts. So I will have the three phasor. Okay, so I will have the three phasor. So using the part transformation, okay, so I will have, this is the quadrature axis voltage. Okay, this is for the stator. I will have the direct axis voltage. Okay, I will have here the 0 voltage. Okay, this is for the stator. Is equal to the transformation matrix. Okay, this is equal to 2/3. Okay, I will have cosine omega t minus 0. This is the element 1 by 1. The element 1 by 2 is the cosine. So I will have omega t minus 2 times pi over 3. And the element 1 by 3 is cosine omega t plus 2 times pi over 3. Okay, and I will have here the stator voltage. This is in the natural reference frame, the voltage V, and the phasor C. So that is the way in order to convert, in order to apply the part transformation, in order to have the in the QD0 reference frame. Okay, yeah. For the second row is the same, but I will change cosine by sine. So instead of cosine, I will use sine. Okay, so minus 0. Okay, I will have here sine minus 2 times pi over 3. Okay, I will have here sine plus 2 times pi over 3. And the last one, and the last row is 1/2, 1/2, and 1/2. Okay, so let's compute the first, the quadrature axis voltage. Okay, let's compute this value. So in order to compute this value, I will have this row times this column, right? this row times this column. Okay, so I will have the stator quadrature access voltage is equal to is equal to, so I will have 2/3 times this one times this one. Okay, so is equal to 2/3. We will have the stator voltage cosine omega t minus 0 plus the phasor V cosine, I will have omega t minus 2 times pi/3 plus the phasor C cosine, J will have omega t plus 2 times pi/3. Okay, so from the previous calculation, we know these values, okay, because we have already computed the voltages for the three-phase system, right? We have already computed these voltages for the three-phase system, okay? So I will have this value is 537.598 345. This is this phase, okay? Because I am analyzing the steady state condition, the time is equal to 0. The time is equal to 0 because this term is equal to 0. Okay. For voltage V, I will have negative 70.105. Okay. 369. And for the voltage C, I will have negative 400. I will have 67.492. Okay, 978. Okay, so therefore this voltage is equal to 537.598. Okay, 345 volts. Okay, this is my first term. Okay, so let's continue with the direct access voltage. Okay, so for the second term, for the direct access voltage, 2/3. So I will have 2/3 this row times this column, right? So I will have 2/3. This is the phasor A. I will have sine. I will have plus the voltage V. Okay, I will have sine. This is omega t minus 2 times pi/3. Okay, and the last one is the voltage C sine. Okay, I will have omega t plus 2 times pi/3. Because I am analyzing the steady state condition, this t is equal to 0 because this term is 0. Therefore, this term is 0 and this term is 0. This value is this voltage. This value is this voltage. And this value is this voltage. Therefore, the direct access voltage is equal to negative 229.431844. And this is my second and this is my second term. For the last term, okay, for the last term, I will have this voltage is equal to 1/3, okay, because I cancel off. I will have the stator, the phase angle, the line to neutral voltage plus the voltage B plus the voltage C. Okay, so what is the voltage A? Is this value. What is the voltage B? Is this value, and this is the voltage C. Okay, so I will sum up these values. Okay, and this is equal to 0 volts. Okay, to 0 volts. So I will have my first. This is the quadrature axis voltage. This is the direct axis voltage, and this is the zero axis voltage. Okay. So therefore, I have the three values. Okay, I have the three values. So I need to compute two per unit values. I am working on the stator side. Okay, I am working on the stator side. I need to compute the per unit values. Okay, I need to compute the per unit values. Okay, so for that I need to select a base. Okay, so I will say the base voltage. Okay, on the Park transformation for the stator is equal to the square root of 2 times the stator voltage base. Okay, so this is equal to the square root of 2, and this voltage, we have already computed this voltage, is 398.372. Therefore, the base is equal to 563.383. 0, I will have here 85 volts. Okay, this is the base. So let's compute the per unit values. Okay, so let's start with the quadrature axis voltage. So by definition, the per unit value is equal to the actual value over the base. Okay, and this is the base, 563.383. 0. I will have here 85. This is the base. Okay, what is the actual value? The actual value is 537.598, 345. Therefore, the quadrature axis voltage in per unit value is equal to 0.900. I will have here 954,233 per unit. Okay, let's continue with the direct axis voltage. Okay, so once again, by definition, is equal to the actual value, 229. So I will have 229.431,842. This is the actual value, and the base is 563.383,085. And this is equal to, this is the direct axis voltage in per unit value, is equal to the negative 0.407, 239 per unit. And finally, the last voltage, of course, is equal to 0. Okay, so following the methodology, so let's make a look in this part. Okay, so this is using the Park transformation, I have the QD0 reference frame, but only for the stator. I need to do the same for the rotor, right? I need to do the same for the rotor. Okay, so we will continue. I have already finished for the stator side. Now I want to continue with the rotor side, okay? But let's make a loop. I am in the first step only, okay? I am in this step. Okay. Okay, so let's continue with the rotor side. Okay, let's continue with the rotor side. Once again, if I need to compute the actual values and the electrical quantity. So let's remember, from the mechanical quantities to electrical quantities, you will use the number of poles, okay? And in order to refer from the rotor side to the stator side, I will use the slip. So I will start from the rotor side. Okay, this is the mechanical speed. So in order to convert from the electrical quantities to mechanical quantities, I will use the number of poles, okay? So this is equal to over the number of poles. So I will have 2 times 376.991 over 4. And this is equal to 188.496. I will have mechanical radians per second. Okay, this is the mechanical speed. Okay, so now I will refer to the rotor side. Okay, this is the mechanical is equal to 1 minus the slip times the mechanical power. So pay attention in order to refer from the stator to the rotor, I will use the slip. Okay, so this is equal to 1 minus the slip from the previous calculation. We know is this value is negative, so I will have becomes positive 0. I will have 0.99,857. Okay, times the mechanical speed 188.496, and the rotor mechanical speed is equal to 207.318. 645. I will have mechanical radians per second. Okay. So I have the mechanical. The mechanical speed. What I need is the electrical speed. So once again, from mechanical quantities to electrical quantities, I will use the number of poles. Okay. So I will say the electrical speed is equal to the number of poles over 2 times the mechanical speed, and the number of poles is equal to 4 over 2. And the mechanical, we have already computed this value, 207.318, 645. So the electrical speed is equal to 414.636, 439. This is electrical radians per second. Okay, so in order to compute the actual values, okay, in a similar way, I will have here the rotor voltage. This is the line to neutral voltage. Okay, is equal to, I will have the per unit value 0.127, 856. Guys, turn off the microphone, please. Turn off the microphone. Okay, times the base. Yeah, I will use the same base. Okay, so what is the base? Do you remember? We have already computed this value. Is 398.372. Therefore, for the rotor, I will have the per unit value, the actual value, sorry, and the actual value is 50.934. 134. Okay, so because I have a three-phase system, once again I will use these formulas. Okay, if the phase A is the reference, I need a phase displacement of 120 degrees for the other phases, right? So this is for the rotor. Phasor A is the reference. I will compute phasor B and phasor C. This rotor voltage is this value. Okay, this rotor voltage is this value. So let's compute the values. Okay, let's compute the values. So I will have for the stator, for the rotor, sorry, this is the phasor A. Okay, so I computing the voltage ABC. This is the natural reference frame, but in this case for the rotor, okay, is equal to the square root of 2. I will have here the line to neutral voltage, cosine. Okay, so I will have the electrical speed. This is for the stator, minus the rotor speed, times the time, plus theta plus 0. So notice this is the reference, okay? This is the reference. This is for phasor A. What about phasor B? Okay. What about phasor B? Okay, what about phasor B? So I will have phasor A. This is for phasor B. For phasor B, I will have a phase displacement of 120 degrees. Okay, so the square root of 2. This is the line to neutral voltage. Okay, yeah, I will have here cosine. This is the electrical speed minus the electrical speed, the rotor electrical speed. This is the stator electrical speed plus. In this case, I will include the phase displacement. This is the phase shift. Okay, 120 degrees. And finally, for phase C, I will have the square root of 2. I will have the line to neutral voltage, cosine. And this is the stator electrical speed minus the rotor electrical speed times the time plus 2 times pi over 3. So this is the phase displacement, okay? Therefore, this voltage is this voltage, okay? Because I am analyzing the steady state condition, these terms become 0, equal to 0, and equal to 0, okay? And from the previous calculation, theta is negative. We'll use this color. So I will have theta r is equal to negative 2.395 813. Okay, this is theta. This is this value. Okay, therefore I will have the three-phase voltages. Okay, I will have the three-phase voltages. Okay, so therefore voltage A, yeah, the phasor A is equal to negative 52.911 572 volts. Yeah, for phasor B, I will get minus 15.872 729 volts. And finally, for phasor C, I will get 68. I will get 68.784 301 volts. Okay, see, this is the natural reference frame. Okay, this is the natural reference frame. So I will use the power transformation. Okay, so I will have the key use 0 reference frame is equal to the transformation matrix times the natural reference frame. Okay, so this is the natural reference frame. What I need is to compute in the DQ0 reference frame. Okay, so for that I will have here the voltage. This is the quadrature axis voltage. I am working on the rotor. Okay. This is the direct axis voltage. And this is the zero axis voltage. Okay. Next, I need the transformation matrix. Okay, so I will have cosine. I will have the electrical speed, the stator electrical speed, minus the rotor electrical speed times the time, minus 0, because it's the reference. Yeah, this is the term 1 by 1 of the matrix. Okay, the element 1 by 2, I will use another color. This is the cosine. Okay, this is the cosine, so I will have the stator electrical speed minus the rotor electrical speed. Yeah, I will have a phase displacement 100. Yeah, this is the element 1 by 2. And the element 1 by 3, I will copy down. Okay, so I will have cosine. This is the element 1 by 3, okay? So I will have the stator electrical speed minus the rotor electrical speed. Yeah, I will include the phase shift, 120 degrees, okay? Yeah, this is my first row. What about my second row? I will change sine, sine, and sine. Sine of this quantity here. Sine of this quantity here and sine of this quantity here. This is the second row. And the last row is 1 over 2, 1 over 2, and 1 over 2. I will close the brackets, okay? So let's open the brackets. I will have here the voltage A, the voltage B, and the voltage C. So from the natural reference frame, using the transformation matrix, I will get the DQ reference frame. Okay, this is for the rotor. Okay, so in order to compute the quadrature axis voltage, I will multiply this row by this column, and the same for the second and for the last voltage. Okay, so let's do that. So I will have the quadrature axis voltage. Okay, so the quadrature axis voltage is equal to over 3. Okay, let's open the brackets. Let's open the brace. Okay, so I will have the voltage A times cosine. I will have the stator electrical speed minus the rotor electrical speed times the time minus 0, because this is the reference, okay? Plus I will have the voltage B times, yeah, I will have times the cosine, okay, times the cosine. Yeah, I will have here the stator electrical speed minus the rotor electrical speed times the time minus, I will have a phase shift of 220 degrees. Okay, this is my second term. Okay, the last term is plus the voltage C. I will have here cosine. Open the brackets, open the parentheses. I will have here the stator electrical speed minus the rotor electrical speed times the time. Yeah, I will have here a phase shift of 120 degrees. Okay, this is my first equation. Okay, this is my first equation. Okay, so the voltage A, we have already computed this value, is negative 52, 500 11, 572. The voltage V is equal to negative 15, 872, 799. And the voltage C is 68, okay, 68.784, 301. This is volts. Okay, so this term, because I am analyzing once again the steady state, this is 0. This is 0 because T is equal to 0. And this term is equal to 0 too. Okay, so therefore the quadrature axis voltage, is equal to negative 52.911, 572 volts. Okay, so for the second equation, instead of the cosine, I will use the sine. So for the direct axis voltage, instead of the cosine, I will use the sine. Okay, so therefore, the direct axis voltage is equal to 448.876, 597 volts. Okay, and finally, for the zero axis, voltage, I will have 1/3. This is the voltage A plus the voltage B plus the voltage C. And this is equal to 0, of course. Okay, and this is equal to 0. That is the reason I will have in the DQ0 reference frame. This is the part transformation. Okay, this is the part transformation. Okay, if I have the actual values, what I need is the per unit values on the rotor side. Okay, this is the actual values. Okay, this is the actual value. This is the actual value, and this is the actual value. What I need is the per unit values. Therefore, I need to select a base. So we have already selected the base. Do you remember? This is the base? Okay. This is the base, but I need to convert for the rotor side. Okay, I need to convert for the rotor side. So I will say the quadrature axis voltage. This is the actual value, the per unit value, sorry. By definition, the per unit value is equal to the actual value. The actual value is this value, and this value. This is the actual value, 911, 572. This is the actual value over the base, and the base is 563. We have already selected this base in the previous calculation. So 0.383, 0.85. Therefore, the per unit value, this is for the rotor side, the per unit quantities, okay? So this is equal to 0.093918 per unit, okay? What about the direct access voltage? The direct access voltage is equal to, what is the value? What is the actual value? Is this one, right? So I will have 48, okay, 0.876, 597 over the base, 563.383, 0.85. So this is equal to 0.086, 756 per unit. Okay, and the last one, this is the zero axis voltage is equal to 0 per unit. Okay, so I have the per unit values. So I have already finished the first step. Let's back to the methodology. Okay, so I have finished only the first step because I have for the stator and for the rotor the QD0 voltages in per unit values. This is my first step. Okay, so my first step is done. Okay, so let's continue with the second step. Once I have the voltage, I will compute the fluxes. Okay, once I have the voltage, I will compute the fluxes. Okay. So from the fluxes, I will split up in two parts. The first part is the stator side, and the second part is the rotor side. Okay. So for the stator side, the fluxes are broken down in three equations. Okay. This is equation number 1. This is equation number 2, and this is equation number 3. For steady state analysis, the derivatives are equal to 0. That is the reason I have the red color, right? The derivatives are equal to 0. Okay, and this is the dynamical model. Okay, and this is the dynamical model. So a set of equations for simulated an induction machine in DQ model in the arbitrary reference frame. I will have, in this case, 6 equations. Okay, so the flux linkage equation, okay, for the stator side is this one. So once again, what is known and what is unknown, and what is data, by the way. Okay, so let's analyze what is data. So let's clear this part because I need the room. Okay, so what is data? From the previous calculation, we know the quadrature axis voltage, the direct axis voltage, and the zero axis voltage for the stator. What about the rotor? We know the quadrature axis voltage, the direct axis voltage, and the zero axis voltage. Okay, this is the data. What is unknown? What are the unknown variables? So you will have the rotor flux in the DQ0 reference frame, the stator flux, okay, in the DQ0 reference frame, and the magnetizing flux. And the magnetizing flux in the QD0 reference frame. Okay, so I will have 8 unknowns. Okay, and for the stator side, I will have 3 equations. Okay, so this is only for the stator side. So I will have the flux in the quadrature axis. This is my first equation, the direct axis flux and the zero axis flux. Okay, so for that, in order to substitute the data, I need to know the base speed. Okay, and besides, for the rotor, I need to know the rotor speed. So for this case, I need to know only the base speed. Okay, so the base speed is equal to times pi and the frequency of operation. In this case, I will have 60 hertz. Therefore, is 376, 99, 112. Okay, and this is equal to the speed. The base speed is equal to the rated speed. And besides, I will need the rotor speed. So the rotor speed from the previous calculation we know is for 414. Okay, so the rotor speed from the previous calculation is equal to 414. I will have 636, 439. Okay, so this is unknown, this is unknown, this is unknown, and this is unknown. 3 unknown variables. QADS. So what about these 2? This is unknown. So this is unknown, this is unknown, and this is unknown, this is unknown, and this is unknown. So I have 3 equations, 5 unknown variables. Okay, this is for the stator side. So I will have the base speed is equal to 376.99, 112, and this is equal to omega. Okay, and the rotor speed is equal to 414.636, 439. Okay, so therefore, by the way, this is equal to 0. This is equation number 1. This is equal to 0. This is equation number 2 for the steady state analysis, and this is equal to 0. Okay, so substituting the data, substituting these values, Okay, so substituting these values. So I will substitute this value. Yeah, substituting this value. Okay, this value. Do you remember we have already computed the quadrature access voltage and the direct access voltage and this value? Okay. So we have for the stator and from the rotor. We know these values, right? Okay, so let's substitute these values. My first equation. Yeah, substituting the values in my first equation. Okay, so I will have my first, my second, and third equation. Okay, this is 0, this is 0, this is 0. So this speed is 376.99,112. The same here, the same here. Okay, so the quadrature access voltage, we have already computed this value in per unit value 0.900, 0.954, 233. Okay, the direct access voltage is negative 0.0, 0.400, negative 0.407, 239, and this is equal to 0. Okay, omega is 376.99112. Omega base is equal to the same value, 376.99112. And the rotor speed is equal to 414.636,439. Okay, the stator resistance. Okay, the stator resistance. Okay, so the stator resistance is equal to 0.00779. And the stator reactance, according to the manufacturer, is equal to 0.07937. Okay, so this is unknown. This is unknown. Okay, 2. This is unknown. I have 5 unknown variables. I have only 3 equations. That is the reason I will use the rotor side too. So this is the equation for the rotor. So let's call this equation 4, 5, and 6. The derivatives are equal to 0. Okay. This speed, the base speed, is this value. Okay. The rotor speed is this value. Okay. The rotor resistance. Okay. The rotor resistance is equal to 0. I will have 0.0082. The rotor reactance is equal to 0.4. Okay, so I have this. What about this voltage? We have already computed these voltages in the previous calculation. Okay, so these voltages are equal to, for the quadrature access voltage, this is negative 0. I will have 0.939.18. This is my first voltage. For the direct access voltage, I will have 0.086, 0.086, and I will have 556. And for this voltage is equal to 0. Yeah, what else? I will have, this is unknown, and this is unknown. Okay, yeah, this is terms. In the previous equation, we have already have these terms. Okay, so I have eight unknowns. I have 6 equations. Okay, I have 8 unknowns. I have only 6 equations. Okay, therefore, what is missing is 2 equations. Okay, so the 7th equation, and this is the 8th equation. Okay, so pay attention to this part. This is the stator reactance. This is the rotor reactance. So we know these values from the manufacturer, okay? The quadrature access voltage and the direct access voltage, so from the previous equation, okay? And this is a no 2. So the only new variables is this 2, 1, because this is constant. How to compute this constant? Using this formula, okay? Using this formula. So the quadrature reactance is equal to the direct reactance, direct access reactance, and this is equal to 1 over the magnetizing inductance. From the manufacturer, we know this value is equal to 4.1039 plus 1 over, I will have the stator reactance. This data come from the manufacturer, 0.07937. And the last one, the rotor reactance, is 0.4. I will have here the inverse, and this value is 0.065 177 per unit. So substituting this value here, I will have A unknowns and A equation. But in this case, I don't need initial condition because it's linear equations, okay? In the previous set of equation, I have a nonlinear equation. In this case, it's linear equation. Okay, so solving the A by A equation, okay, solving the A by A equation, I will get for the stator, okay, the quadrature access flux is equal to 0.407 809 per unit. Okay, the direct access flux is equal to 0.960 760 per unit. Okay, and the zero flux is equal to 0. This is for the stator. What about the rotor? For the rotor, I will have the quadrature access flux, the direct access flux, and the zero access flux. This is for the rotor. And for the rotor, I will get 0.855 690 per unit. Okay, for the direct access flux, I will get 1.018 813 per unit, and the last one is equal to 0. The last two quantities is the magnetizing flux. This is the quadrature flux, is 0.474 311 I will have here per unit, okay? And the direct access flux is equal to 954 961 per unit. Okay, so I have already finished my second step. So let's back to the methodology. Okay, so once this is my first step, is over. Okay, the second step, once I have the voltage, I have already computed the flux. Okay, with the flux, I will compute the current. Okay, with the flux, I will compute the current. I have already computed the fluxes. Okay, so in order to compute the current, this is for the stator. Okay, see, this is the stator reactance, and this is the flux. So we have these values. Okay, so we have these values here. Okay, so substituting the values, I will get the current. Okay, so substituting the values, I will get the current. So this current, the stator current is equal to negative 0. I will have 837 873 per unit. Okay, for the direct access current, I will have 0. I am only substituting the values, right? 0.073 063 per unit. And the last one, of course, is equal to 0. This is for the stator. What about the rotor? For the rotor, the same. In this case, in this case, substituting the rotor reactance and the fluxes. We have already computed these fluxes in the previous step. Okay, so I will get the currents. The current is equal to 0.953 448 per unit. This is the quadrature axis current. The direct axis current is equal to 0.15. I will have 963 per unit. Of course, this current is equal to 0. Okay, so let's back to the methodology. Let's back to this methodology. Okay, so this step is over, this step is over, this step is over. So with the current and the voltage, I will compute the power. With the current and the voltage, I will compute the power. Yeah, the stator active power, the stator reactive power, the rotor active power. So pay attention. We have already computed these voltages for the stator and from the rotor, and we have already computed the currents. So we know these values. Okay. So therefore, substituting the values, I will have the stator active power is equal to 0.829,280 per unit. Okay, the stator reactive power is equal to 0.271,495 per unit, and the rotor active power is equal to 0.075,697 per unit. Okay, this is in per unit values. If I want the actual value, I need to multiply by the base. 2.21 MVA times 2.21 MVA times 2.21 MVA. Therefore, I will get the actual values. Do you remember from the control strategy, we know the rotor reactive power is equal to 0, right? So I will have this value is equal to 1.83 megawatts. Okay, I will have this value is 0.6 megavar, and this value is 0.17 megawatts. Okay, so I need to verify the initialization. Okay, so let's back to the reference set point. Let's back to the reference set point. Okay, what is the set point? 2 megawatt is the power grid, and 0.6 megavar is the reactive power grid. Okay, this is the set points. I need to verify 2 megawatts and 0.6. Okay, so let's back. Okay, let's sum up this value plus this value. This is the power, the grid active power. And this 1.83 plus 0.17 is 2 megawatts. Okay, and the reactive power grid is equal to 0.6 megavar. Therefore, the initialization is right. Okay, therefore the initialization is right.